Hello, I'm Alexey Fedorov and I'm wearing a hat of That TD Fellow today. That means you're watching TD Screencast episode number 4. As mentioned in the previous episode, today we are going to implement a pathfinding algorithm. Specifically, our first problem in the pathfinding theme will be the following. We are given a directional graph that consists of nodes and edges between them. We are given two nodes, start and finish. We need to answer such questions. Is there a path from start to finish? And if there is, what this path is? I need to make a remark that we clearly don't have to return shortest path, just any path will be sufficient. We will tackle shortest path problem in later episodes. Now I think we can start. As always, I will begin with writing some tests. And defining a module. Okay. So now I can say that it finds a path and to make a code to find path. Find path will accept graph, start and finish. Graph will be probably empty graph for first test, and we'll have something like first node and second node for finish. An empty graph will be an empty hash of int to array of int. What it means that key represents a node that edges are coming from, and an array of ints represent ending nodes for those edges. Okay, so that should not compile. And now we need to define this method. Graph, start and finish. Okay, so now we can say that it should equal to, let's do a response now. So response will contain two values, if the path is actually found, and if it is, then the path. So it is false and empty. And empty is empty array of int. Okay, that should fail. Now we need to return those values. Now it succeeds. Okay. So let's specify now another edge case is when we want to travel from the same node to the same node, which means that we have a path which will contain only this node. Even if graph is empty, we don't care. We assume that nodes exist and all possible nodes are there that you can name, but graph actually defines edges between them. So empty graph means that all possible nodes exist, but there are no edges between them. So that should fail. Okay. And now we need to add pretty obvious condition that we'll check for this case. If start equals finish. Okay, that works. So now I can specify some simple graph that has only one edge from 1 to 2, and we want to find a path from 1 to 2. And then this should equal to true and 1, 2. That of course will fail, okay? And now my observation here is that the simplest thing that I can do is to check that if graph has key start, then if graph from start dot first equals finish, which means that our first edge goes directly to finish, then we can return true, start and finish. Okay, that works. Now let's see what happens when we want to go from 2 to 3 here. It should return false and empty. Okay, that works. So now I want to break my code, and I can do that by reusing this test case and changing the data a bit. For now I would say that 1 leads to 3 and 2, and since we use dot first there, it will try to go for 3 and it will be not there. So that should fail. Okay, now I can replace dot first with dot includes. Okay, it succeeds. Now what? Now kind of very interesting thing. I can actually make a longer path now. So from second to fifth. And I want to go from second to first to fifth. And the result should be 1, 2, and 5. That shouldn't work. Okay, that does work as expected. So now I need to check if the next node is actually allows me to go there. Let me simplify a case a bit so that I can implement it with less code, like this. So I think that, yeah, okay, here. So nodes equals graph from start. Then if nodes dot size more than 0, node equals graph nodes from 0. So we pick the first node that we have there, which is already not finished, because we know that otherwise we would have returned earlier. And now we want to check if this node leads to finish. So we'll basically use something like this here, but a bit differently. Now start but node includes finish, and if it is, then the node here and start here. Okay, it works. So I think it will actually work even if we have multiple things here. because we have includes there. Okay. Now we can break this test by using, instead of 2, 3 here. And actually we can make it pass by just copying this if and saying 1 here, 1 here, and should succeed. Oh no. What happened there? Using hash key 3. Yeah. So I need to have if here. Okay, that succeeds. So one interesting thing about this is key that we actually don't need this, because we use includes on the result, which means that we can provide a default value of empty, which will look like this: dot fetch start, comma empty, and we don't need this condition anymore. Can remove practically this, and we should be able to remove this the same way. Okay, that should still work. No, that doesn't work. Yeah, and here. Okay, it works. Now, if you look at those two ifs, we can make them entire duplicates by extracting a variable. That should still work. And they are duplicates now. That means that it's actually while. And we don't need second section. Okay, that works. So now we should be able to support all the numbers here. So if you notice, interesting thing here is that this and this is quite similar. And probably we can even say if node equals finish, return true, start finish. This makes it the same thing as here, which can be converted to this kind of if. Okay. And I actually think that we don't need this anymore, because this condition is verified by this line. Okay, it still succeeds. Interesting. Now we can do the thing. Because we don't need a loop variable anymore here, I suppose. Okay, that still works. Now let's break our code by having more nodes on the path. So now from fifths, I want to go to 8 and 9. I want to go to 8 eventually. and the path should be 1, 2, 5, 8. Okay, as expected it fails. But now if you look here, this line and this line is practically the same. And if you ask me, this line actually can be still the same if you convert this if to each. So basically, if I say here the same thing. Not really. It should be node 2, and then I should have node, comma node 2 here. Like this. Okay, like this. So that's still fail, of course. But now what I can do, I can just do the same thing, right? Node 2, empty node 3, start node 2, if node 3 equals finish. So it succeeds. So you probably see the pattern, right? My feeling that this is actually a recursive call. Ok pass equals find pass, graph start, node finish. And I don't think we need this condition because it will be handled by recursion. And now return true, start plus pass if okay. Okay, it works. And actually I assume it works now for everything, even if I will have more of those things there. Yeah, no, not really. Yeah, I need to go to 11 now. Okay, that works. Now there is still one thing that can break our algorithm, is the graph with loop. So for example, if from 2 I go back to 1, somewhere here. Yep, failure, segmentation fault. Yeah, return false empty if visited includes start. So if you already have been there, then there is no point in going there second time. And visited equals empty here, and we'll pass it here as a visited plus start. Okay, it works. It actually works now for everything, I'm pretty sure. Because I don't know how to break this algorithm anymore. And the only thing that now bothers me is that we pass a lot of arguments here. So let's convert this module to class. But provides the same interface. So start will change, but finish will not change, and graph will not change. So new graph finish dot find path start. Initialize with graph and finish. Create some private getters. Here we don't need graph, we don't need finish, we still need visited. And here in the code we need to change it. That should still work. Okay, it does. That's pretty nice. So another thing that bothers me is that we actually copy a lot of times visited, and I don't like that. And visited actually is not scoped to one branch of recursion, it is scoped to the whole algorithm, the whole execution. So we might as well just do something like this. We can make it mutable. Didn't quite work. That was typo. Okay, that still works. Now, last bit of small refactoring is that I want to extract method walk, which accepts node and does those things. And here walk start. Yeah, should be start. Okay, that works. I think we are finished. It was a pretty simple algorithm. That's actually DFS, depth first search, and it kind of merged on its own while we were driving it with specification. I would like to know if it's possible to do the same with shortest path problem, and we will find out next time on the TD Screencast episode.